by Luis. And so we're going to hear about gravitational wave physics by Archisman. Thank you.
Is it on now? I think it's on now.
Yeah, maybe
bring it a bit closer. I'm sure it's on now. I can hear a go. So I'd like to thank the organizers for putting together this wonderful program. It's a pleasure to be here in the center. This is my first time here, and hopefully not the last time, hopefully only the first time. It's I will mainly be talking about standard Siren cosmology. I was initially planning to talk about a bit of fundamental physics with gravitational waves, but I decided to do justice to one topic, and I'm sure that Luis is going to talk a lot about fundamental physics with gravitational waves later in this colloquium. So I'm going to give a brief review of the experiment and observations. I'm going to spend most of my time on standard Siren cosmology and then go over to some future prospects. With apologies to those of you who have listened to my talk last week, I'll begin with an overview of the gravitational wave experiments, the current generation of the current experiments LIGO, Virgo, and Kagra. So most of my talk is going to be on data analysis and observations, but it's I think it's important to appreciate that we are making a really precision measurement with these interferometers, these interferometric detectors, which are L-shaped detectors with laser beams shooting across two perpendicular arms coming back and interfering. And with these interferometers, we are able to measure relative deformations or strains or of the order of 10 to the minus 21. These detectors are typically 4 kilometer long, so that means we are able to measure distances of the order of 10 to the minus 18, so that's a kilometer times 10 to the minus 21, 10 to the minus 18 meters. That's 1,000 times smaller than the nucleus of an atom. On the right, we see the typical sensitivity curve of the detector, which is actually tells us about how high the detector noise is. So, in fact, this bucket in between the high noise areas is our sensitivity region, and we see that we are most sensitive for these ground-based second generation detectors in the region of around 100, 200 hertz, so about 20 to 1,000, 2,000 hertz. We currently have a network of 5 detectors which are operational or which are going to be operational as soon as our next observing run starts. And of the 5 detectors, 4 of them are really science detectors, and there's a GEO 600 detector in Germany, which is mainly used for testing various components that eventually get installed in the other detectors. And a 5th science detector is planned to come up in India. The data from all of these detectors is analyzed by a global collaboration with from around 30 countries, from 30 countries all over the world, including Brazil here. The gravitational wave sources which we expect in this region, in the region of 100 hertz-ish, they fall into 4 categories. So these also define 4 of the data analysis techniques that go into our gravitational wave data analysis. They are compact binary coalescences, so mergers of binaries of black holes or neutron stars, which we have already detected. However, there are other sources which we also expect in this band, which we have not detected yet. These are bursts. So these would be explosions which are not really modeled, for example, explosions from core collapse supernovae. Continuous gravitational waves, so gravitational waves from, for example, a neutron star which is not perfectly symmetrical spinning. Because it's not perfectly symmetrical, there's an asymmetry, because of this asymmetry, there's a change in the quadrupole moment, which is the sense of gravitational radiation. So we should see very continuous sinusoidal gravitational wave of constant frequency from these sources. And moreover, we also expect to see a stochastic gravitational background. A part of the stochastic gravitational background is expected to be cosmological, coming from the very early universe, but in the LIGO-Virgo band, it's expected to be drowned in an astrophysical background coming from the superposition of all other gravitational wave sources. So these compact binary mergers, they go through, they are the last stages of the merger of a binary that has probably been in its orbit for millions of years. And as it has been going around, it's been radiating gravitational radiation. And due to this energy loss, it has been falling in. And as it has been falling in, it is moving faster and faster. So it goes through the final cycles of in spiral and then plunges into a merger. And finally, one black hole is formed, which slowly settles into its final state, giving out the last bits of gravitational radiation and settling down into its final state. The gravitational signal from this merger is a characteristic chirp signal, so-called because it's of the fact that its amplitude as well as its frequency increases with time. And on the plot in the bottom over here, we see how this particular signal from the first detection swept chirp in this time frequency plot, both the frequency increased with time, consistent with the fact that we are in the 100 hertz region and with a period of about 0.3 seconds. Now, for these signals, the signal can be modeled very accurately by a combination of analytical and numerical methods. In fact, two of the organizers who are here are some of the authorities on modeling these signals in different ways. Because this signal can be so accurately modeled, it is possible to search for these signals even when the signal is as small or smaller than the noise around it by a method called matched filtering. So I think the animation will work. So here we see a train of data with some signal within it. You do not really see the data within the signal, but as you run a template through the data where the signal is located, we see a peak in the cross-correlation function telling us that there is some something interesting, some data within the signal at that point. Of course, we do not only want to know where there's a signal where there isn't. We want to know what kind of source the signal came from. And the signal carries information about the parameters of the system. What kind of parameters of the system? The intrinsic parameters of the system that really belong to the system, like the masses of the components which are about to merge, the angular momentum of these components. These are for black holes. And if you're going to neutron stars, also tidal parameters, how these neutron stars, how easily these neutron stars can be deformed. And if you want to look beyond standard physics, then one can also put in additional parameters beyond generativity. And there are also extrinsic parameters, which are not parameters of the system itself, but which are more about where we are located with respect to the system. So the distance to the source, the sky location, the inclination angle, how the source is oriented with respect to us, and the polarization, the relative polarization between two directions given a coordinate system, and such. So with these two aspects, a rapid search and a rapid as well as a low latency parameter estimation. We have a complete workflow for data analysis of compact binary coalescences. So as the signal is coming in, we search through the signal, try to find interesting triggers. We try to rank the triggers. And of course, some of the triggers are false. We try to characterize triggers by a false alarm rate. And on the interesting triggers, we then carry out parameter estimation at low latency, which is given out to astronomers for electromagnetic follow-up in case there's a possibility of a coincident electromagnetic radiation. And on a higher latency over a longer time, we perform thorough Bayesian parameter inference, and out of this we extract essentially the results that come results on fundamental physics, astrophysics, and cosmology. Between 2015 and 2020, we have had 3 observing runs with increasing sensitivities. Our sensitivities are often characterized by the binary neutron star range, the distance to which we can see binary neutron stars given a sensitivity curve. And as you can see, the binary neutron star range has been increasing over the 3 observing runs. And the detection rate has also been increasing over the 3 observing runs. And we have ended up with about 90 detections at the end of the 3rd observing run. The discovery of gravitational waves in GW 150914, it was of course the first direct detection of gravitational waves. It was the first direct observation of a black hole. It was the discovery of a class of heavy black holes of mass greater than 30 solar masses. These black holes were not expected in conventional astrophysics. It was the first observation of a black hole in a binary, and it was the first observation of a black hole forming. The 2 black holes merged and formed a remnant black hole, and we could really see how we can really see how a black hole really oscillates as it is formed. And this tells us, as we heard yesterday, about fundamental physics and no-hair theorem. We already had 2 more signals in the first observing run, and one thing I'd like to point out here is that signals which are of lower mass, lighter signals, they merge at higher frequencies, so they tend to spend more time in the observable band. One can do a calculation to see this, but there's also a simple way to see this. This comes from a very simple scaling, that in general relativity there's no scale other than the gravitational constant. So one can work with units where the gravitational constant is set to unity, and in these geometrized units, mass and time have the opposite. Mass and time have the same scaling dimension. So mass and frequency have the opposite scaling dimension, and frequency just goes as 1 over mass. So heavier black holes, they coalesce at lower frequency. Lighter black holes, they coalesce at much higher frequencies. And we had many more similar detections in the second observing run. Of course, the highlight of the second observing run was the binary neutron star merger, GW 170817. And here we see the gravitational wave chirp from the binary neutron star merger. It's a much longer signal. It goes on for about about a minute or longer, and already telling us that it's potentially a binary neutron star. But because it's not just gravity, because there's also matter colliding, one can expect other kinds of radiation, for example, an electromagnetic radiation, or even neutrinos following the merger. In fact, we were not so lucky to observe neutrinos from this, but after about 2 seconds after the gravitational wave signal, there was a gamma ray burst, and about 10 hours later, this patch of the sky was being followed up, and an optical counterpart was observed. The optical counterpart was quickly identified to a host galaxy, and this optical counterpart slowly or faded away from optical to near to far infrared, eventually emitting radio afterglows much later. So essentially, this counterpart was observed in practically all bands of electromagnetic astronomy. This gave birth to multi-messenger science with gravitational electromagnetic waves and confirmed binary neutron stars as progenitors of short gamma ray bursts. It demonstrated that they were prolific sites of heavy element formation. In the plot for the kilonova, which you saw earlier, one can see these spectral lines, and from these spectral lines, one can infer that, what kind of heavy elements exist in these in the region after the merger. And it constrained the speed of gravity with respect to the speed of light. The gravitational electromagnetic signal, they arrived essentially at the same time after traveling for millions of years, which demonstrated that gravity and light propagate with the same speed. It provided an access to the elusive neutron star equation of state, which is otherwise very difficult to measure either on laboratory experiments or also difficult to calculate by lattice QCD techniques. And finally, it provided a novel measurement of the Hubble constant in cosmology, which is going to be the topic of much of today's talk. Some of the more recent highlights from the third observing run were, these are some of the detections from the first half of the third observing run. And among the exceptional ones are GW 190425, which is a potential BNS, but we do not really know whether it is really a BNS because we could neither measure tidal parameters nor see a counterpart. However, its masses are consistent with it being a binary neutron star merger. However, it is a bit heavy compared to all other binary neutron star mergers which have so far been observed in electromagnetic astronomy. Then there was GW 190814, a highly asymmetric system for which the lighter object was in the putative mass gap between neutron stars and black holes. This even further had a mass ratio of greater than 9. So the heavier object was 9 times heavier than the lighter object. And with these high mass ratios, as we also heard yesterday, we can infer higher modes in the gravitational wave signal. And for this particular system, we had a clear identification of the 3-3 mode in the gravitational wave signal. And perhaps the most interesting one was GW 190521, with black holes, with the progenitor black holes of masses around 85 and 65 solar masses, and the remnant in around 150 solar masses, clearly in the intermediate mass black hole region. In O3b, we observed at least 3 mergers of black holes and neutron stars. So O3b has also given us something new. And here in the colored contour, we see the 3 objects which are clear, in which clearly one of them is a black hole masses of around 20-30 solar masses, and the other one neutron star, much lighter. There are a few others where we do not know whether one of the objects is in the mass gap or is really a neutron star. So we have of the order of 90 events, 90 detections now. We can start doing a lot of science where the number of detections matter. And these include some of the tests, some of the tests of generativity which we are performing, where we can combine or stack information up from multiple observations. Here we see a plot that constrains from propagation effects various parameters that are inconsistent with Lorentz violation, and essentially one parameter which is consistent with Lorentz violation but gives a mass to the graviton. So these terms can be constrained, and we have a constraint on the mass of the graviton, which you see over here. Then with these large number of observations, we are able to infer the population, the astrophysical population of these binaries. And the plot over here shows the mass distribution of the primary, of the heavier of the two objects which are merging. And it, although it is not very clear at this stage, we kind of see a small feature, a small bump in the mass distribution at a certain mass beyond the power law decay. And we have cosmology from gravitational wave observation. We have cosmology from these observations where we also combine information from various events. And here is the latest measurement of the Hubble constant, which is, as I said earlier, going to be the topic of the bulk of my talk. With this introduction, I'm going to go over to standard Siren cosmology. And I'll explain what standard Sirens are, and then how we use, I'll talk about bright and dark standard Sirens. We already heard about some of this on Monday. And then I'm going to talk about the current results. So what are gravitational wave standard Sirens? Probably the first thing that you notice when you see this signal is that the signal is characterized not only by an amplitude, but by a phase. So our detectors are sensitive not only to the total intensity or the amplitude, but also to the phase evolution. And essentially this phase evolution carries information about the system, in particular about how heavy the system is. As I said earlier, a heavier system chirps much faster than a lighter system. Of course, that's the leading order effect. There are higher order effects, but the phase evolution gives us a very accurate estimation of the intrinsic mass of the components. Now we can use this mass, which we obtain from the phase evolution, and plug it back into the amplitude, and we know that the amplitude has to fall off as 1 over distance. So together with the phase and the amplitude information, we can estimate the distance to the object directly. Directly meaning with only these gravitational wave signals and without any distance ladder, which is necessary in measuring distance in most of the rest of astronomy. For those of you who are unfamiliar with the distance ladder, this is how it works. We use nearby objects to calibrate objects that are further away, and we then there's an overlap region. We take these objects which are further away to calibrate objects that are even further away. So we start off with very local ways such as ranging and parallax, go over to certain other indicators, and then finally to Cepheid it's a supernova, and which are at each point we try to come up with some sources which are standard or standardizable. So these are standard candles in electromagnetic astronomy. In analogy to standard candles, gravitational waves are standard Sirens, but for standard Sirens, this kind of a distance ladder is not required. We directly measure the distance with the standard Sirens. Now you would also know that with measurement of luminosity distance and redshift, we can come up with a redshift distance relation on the observational side. And on the theoretical side, this redshift distance relation depends on the parameters of cosmology. What parameters in cosmology? The expansion and the acceleration parameters, so essentially the Hubble constant in the local universe, and parameters like the matter density, the dark energy density, and the dark energy equation of state. So with standard candles, one can measure the Hubble constant directly in the local universe. There's also a way of measuring the Hubble constant, not directly but indirectly from the very early universe using CMB data, for example, from Planck. So that measures the Hubble constant in the very early universe, and using a cosmological model such as the lambda CDM model, one can extrapolate that and obtain the value of the Hubble constant in the present epoch. One would imagine that these two values of the Hubble constant would agree. However, as experiments have become more and more precise over the past decade, the Hubble constant from nearby observations and the Hubble constant from cosmological observations have started to disagree, and this disagreement has increased to something around 5 sigma in the recent years. So in some sense, cosmology is calling out for new probes, and gravitation waves is a new probe that can provide insight into this Hubble tension. For a Hubble constant measurement or measurement of cosmological parameters in general, along with the distance, we also need a redshift. The question is, where can the redshift come from? We know in electromagnetic astronomy, there are spectral lines, and by redshift, we mean if an object is moving away from us, for example, due to cosmological expansion, the spectral lines are shifted to a lower frequency. We can see how much the spectral lines are shifted, and we can directly read off the redshift. The question is, are there similar spectral lines for gravitational waves? The answer is, for binary black hole mergers, there are no spectral lines, essentially because there is a redshift. However, the redshift is totally degenerate with the mass of the system. This is same as the scaling that I talked about earlier. There's only gravitational constant and no other scale in the system. So looking at only the frequency, we cannot tell whether an object is heavier or an object is slightly lighter but placed further away so that it's experiencing a higher redshift. Both these effects, and heavier object would merge at lower frequencies. An object that is farther away but lighter but redshift would also be redshifted to lower frequencies. These effects are totally degenerate for black holes. Now, this degeneracy is broken for neutron stars. This is not exactly the case for neutron stars because neutron stars have their internal physics. So one can think of neutrons, tidal effects in neutron stars associated with a certain scale. One can look for resonances within neutron stars. So for neutron stars, these degeneracy is actually broken. So neutron stars can provide an independent measurement of the redshift. But for current detectors, they are practically not usable for measurement. Of course, people are looking into how we can exploit the physics of neutron stars for redshift measurement for the next generation of detectors. But for current detectors, we cannot really rely on the physics of neutron stars. So what can we rely on? We can rely on the fact that although from a single observation we do not have information, a population of neutron stars can be expected to be at around a certain mass. However, if you observe them from farther away, they would be redshifted to a different mass distribution. So if one knows the mass distribution, the intrinsic mass distribution of neutron stars, if one observes a different mass distribution, then one would know how much this distribution has been redshifted, and one can infer the redshift from a population of distributions. Of course, the redshift would be different for each of the different events, but still one can infer from the different events approximately how much the what the redshift distribution essentially is. Until recently, this idea was there only for neutron star mergers, but it has revived in the context of binary black hole mergers as well, and I'm going to talk a bit about that in some of my later slides. The more direct and perhaps the cleanest measurement of the redshift can come only if you have electromagnetic counterparts. So what would happen if you have an electromagnetic counterpart? One would probably be able to associate the counterpart with a host galaxy, and one can read off the spectral lines in the host galaxy and use the and obtain a redshift. There's the possibility of also obtaining the redshift not from counterparts but from galaxy catalogs. So one has not been able to identify a unique host galaxy, but there's a set of possible galaxies from a galaxy catalog that's going to give us some information as well about the redshift, and we are going to talk about that as well. Furthermore, galaxy clustering or large-scale structuring of matter that sets some kind of a scale, and if one observes the large-scale structure at a certain, if one observes a large-scale structure in a certain redshift shell, it is different from the large-scale structure at a different redshift shell. So if one looks at the large-scale structure in the distance space, that essentially carries information about what the redshift of this, of a certain distance shell is. Again, that is a weak information, but it can be exploited possibly for the next generation. I'm going to talk very briefly about that as well. But let's talk about bright standard sirens first. A clean measurement, distance from the gravitational wave observation, redshift from the electromagnetic counterpart or the host galaxy associated with the electromagnetic counterpart gives us cosmology. We had a binary neutron star merger, GW170817, with an electromagnetic counterpart. We could put these two together and we could obtain a first standard Siren measurement in cosmology, which we see here. What is plotted is the posterior probability density. So this is essentially the probability distribution in H0. The peak indicates the most probable value. These are the less probable values. And we compare this with the two measurements in tension. Of course, our errors are much, much wider than any precision cosmology measurement. It's about a 14% error. But the idea is that if one has multiple similar observations, then one can use combined information from many of these and get more and more precise measurements. So typically, the measurement error would scale as 1 over, measurement precision would scale as 1 over square root of the number of detections. If one has a 14% uncertainty at the moment, one would need of the order of 14 squared, which is 200 detections, to go down to a 1% uncertainty. 200 similar detections to go down to a 1% uncertainty. Of course, you might not need a 1% uncertainty to tell which of the two measurements in tension you agree with. There's one important thing to highlight over here, and when I said that the amplitude depends on the distance to the source, I did not tell you that the amplitude also depends on the orientation of the source. So the amplitude depends not only on the distance, but also on the inclination angle of the orientation of a source. In particular, if the source is not face on, but oriented, then the amplitude falls off. So from the amplitude, you do not really know whether the object is farther away or close by and oriented at an angle as opposed to being face on. This results in a degeneracy, in a correlation between the distance and the inclination angle, a degeneracy of the distance with measurement with the inclination, which in turn translates to a degeneracy between the Hubble constant measurement and the inclination. The figure we saw in the previous plot was this particular two-dimensional measurement of Hubble constant marginalized over or integrated over the vertical direction. So we got contribution from this entire from this entire region. However, if one has an independent measurement of the inclination, then one would not need to do the integration over this direction. One can take a slice, one can take a horizontal slice, and one can obtain a much more precise measurement. And with the some of the electromagnetic observations of jets, one could, and the associated jet models, they could already come up with a slightly better measurement of the inclination. If you trust these jet models, then you already get an improved measurement of the Hubble constant. It's important to note that this particular degeneracy between distance and inclination can also be broken by gravitational wave observations alone. If one observes higher harmonics in the signals, that is because the higher harmonics do not fall off in the same way as the lowest order harmonic. And with multiple detectors which make us more sensitive, multiple detectors all over the globe which make us more sensitive to different polarizations, and with signals with higher harmonics, so essentially asymmetric signals, one can hope to break this distance inclination degeneracy better in the future. Let's move over to dark standard sirens. The question now is, what would happen if the electromagnetic counterpart is not observed? As you see, the vast majority, only one signal of these 90 had an electromagnetic counterpart, 1708, 17, yeah, whatever it is. And the rest of them did not have an electromagnetic counterpart. What can we do if no electromagnetic counterpart is observed? Something that one can do is, as I mentioned, one can look for, one can try to identify features in the mass distribution which are robust. So it's argued that the black hole mass distribution is not exactly uniform, but there is a there's an upper cutoff in the intrinsic mass distribution at around 40 or 50 solar masses coming from the pair instability supernova process. And if in the observed distribution, one observes a mass cut in a different range of masses, then that would tell us the redshift distribution of these sources that one is observing. Of course, we do not really know whether there's a sharp mass cut. So a set of papers have shown that even if the mass cut is not sharp, even if there is some feature in the mass distribution, that feature is going to be redshifted and can give us enough information to infer the redshift of the source. An even more agnostic approach is when one does not assume a mass distribution at all. One can try to infer the redshift together with the mass distribution simultaneously. So as we are inferring the mass distribution of the sources which are merging, we also relax the cosmology and we obtain the cosmological parameters simultaneously, giving us already a rough estimate of the cosmological parameters. The second idea comes from galaxy catalogs, and this idea dates back to the first paper by Schutz on standard sirens. The way it works, it's good to go through a set of cartoon animations to demonstrate how it works. So let us first assume that we have a counterpart or an identified galaxy. So one has a distance estimate which comes from the gravitational wave observation, and the unique counterpart or the identified host galaxy gives us a Z value. This gives us a Hubble constant estimate, which is nice and unimodal. We are happy. However, suppose there was no counterpart. So one does not know the exact redshift. However, one knows roughly the region of the sky this event came from. So one can identify a set of galaxies within that sky patch given a certain set of priors. And in this cartoon example, there are 5 possible galaxies. Of course, in reality, there are many, many galaxies and not just 5. So with 5 galaxies in this example, one would obtain 5 peaks in the H0 distribution. Of course, some of the peaks would merge into each other because of the uncertainty coming essentially from the distance, and one would observe essentially a multimodal distribution and not a unimodal distribution. There are 5 peaks here, some of them are merged. So just this measurement is not informative by itself. It does not carry information at all. However, suppose one has a different observation coming from a different part of the sky, a different distance estimate, a different set of galaxies, different set of Z values again taken to be 5, a different multimodal H0 estimate, also not informative by itself. If one stacks up many, many such events, then for all of these H0 estimates, one of the peak is expected to be at the correct location, while all the peaks coming from the incorrect associations are expected to be at random locations. So if one stacks information up from many observed detections, then one would be driven to a joint unimodal result, even though the individual estimates are not informative. This is essentially how this method is supposed to work. In reality, it's a bit more complicated. As we saw already, we are not working with single galaxies, we are working with smear distributions. However, even within a smear distribution, there are overdensities and underdensities. So if we look at a galaxy catalog, we are essentially and use all the Z values from the galaxy catalog, we are essentially tracing the underlying matter distribution. So we are cross-correlating the underlying matter distribution with the distance estimate, the Z values coming from the matter distribution with the DL estimates. And moreover, one can give different weights to different galaxies. So one can give more weights to brighter galaxies, and using this one can improve the efficiency in the method. One can, for example, give a weight in proportion to the luminosity in certain band, in a visible band, if one assumes that these gravitational wave mergers are correlated with the star formation rate, or in an infrared band if one is more agnostic and wants to assume that these gravitational wave mergers are correlated with the total mass of the system. And that leads to an improvement in the measurement. So, an additional complication in this measurement comes from selection effects. So, selection effects will be there on both the gravitational wave side and on the electromagnetic side. Let's first talk about the gravitational wave selection effects. Gravitational wave selection effects would come due to a limited sensitivity of our gravitational wave detectors. So we would not observe all the signals, we would observe only the nearby signals. And if one observes only the nearby signals, even looking at the linear Hubble law dl H0 is ZC, if one has only small values of Z, if one has only small values of distance, one would be biased to high values of H0 just by this linear relationship. In order to undo this, one needs to in order to undo this bias, one needs to calculate the detection efficiency, which is obtained by integrating over all the detectable data sets and putting this detection efficiency in the denominator of the likelihood. However, in order to calculate the detection efficiency, one has to assume the source population parameters in order to know what kind of sources we will detect. We need to, in order to integrate over all the detectable data sets, we need to know the source population parameters. So this is how the first method that I talked about, inferring H0 from source populations, automatically enters the second method, inferring H0 from galaxy catalogs. The idea is to infer the perfect thing to do would be to infer H0 and a population parameter simultaneously, which is the direction to which we are converging. On the electromagnetic side, there are also selection effects which come from a limited depth of the telescope, leading to incomplete galaxy catalogs. And in order to take care of this, in addition to the in-catalog term, one has to add a contribution expected from the out-of-catalog term. And essentially, with the taking care of the gravitational and the electromagnetic systematic effects, one can expect to obtain an unbiased value of H0. The first realistic dark standard Siren measurement essentially came from a paper led by the Dark Energy Survey collaboration together with the LIGO-Virgo collaboration. And we heard about the survey yesterday from Jesse. And they actually coined the term dark standard Sirens, which has now become very popular and we are using. So this is the first measurement coming from one very well-localized black hole, GW170814, located in a patch that was very thoroughly followed up by the Dark Energy Survey. Moving more towards the current detections, we have H0 measurement by the LIGO-Virgo collaboration coming only from the source population. So here we do not use any galaxy catalogs. We assume only a mass distribution, that is a power law and a Gaussian peak, and we leave the power law free, the location and the width of the peak free, the relative strength free, and we infer simultaneously the cosmology and the population parameters. We already obtain an improvement with the dark standard Sirens over the GW170817 value. Putting in galaxy catalogs, unfortunately, we do not put in the DES catalog here. We only put in catalogs, the Glade catalog, which is more all sky but not as deep as some of the surveys like DES. We obtain an even further improvement in the H0 measurement. Of course, we are trying to make a precision measurement, so it's important to assure that systematic effects are smaller than statistical uncertainties at the current stage. So we try to assess all our systematic effects. It turns out that at the current stage, systematic effects coming from population parameters is smaller than systematic effects from galaxy catalog parameters. This is essentially because we do not really have deep galaxy catalogs. So the situation is expected to change with more in-catalog information. And in my group, a student is trying to assess what kind of when systematic effects from galaxy catalogs are going to become important. A summary with results of inclusion from dark standard Sirens is over here on the left. You see the result from O2 only, with only a slight improvement over the GW170817 results, and the results from O3, which is a much stronger improvement, again showing us that we are getting we are strongly influenced by the number of detections which we are using. I tried to put these results together in a in a plot like we have seen before, and here we already see the dark Siren contribution. Maybe if we have enough detections, we'll be able to resolve the H0 tension with subsequent observations. Once again, we are trying to attempt a precise measurement. We have to be very concerned about accuracy. So we have to be we have to understand all kinds of systematic effects which can come from modeling of which can come from peculiar velocities in the on the electromagnetic side, and other uncertainties from galaxy catalogs, as well as on the gravitational wave side from waveform modeling or detector calibration, although these uncertainties are currently expected to be much lower than the other sources of error. So hopefully with more sources, with rapid follow-up of some of the sources, with early warning that is predicting that a BNS is going to merge even before it has the merger has taken place, we can have more counterpart detections. On the galaxy catalog side, the limitation is incompleteness of galaxy catalogs. Hopefully with upcoming surveys, we are going to have deeper catalogs providing us better redshift information. There are also some prospects of using not galaxy catalogs, but catalogs of galaxy clusters. Of course, we would not have very precise redshift measurement, but given our gravitational wave uncertainties, probably the way galaxy cluster catalogs trace the underlying matter distribution, that may be sufficient for cross-correlating with gravitational wave distance observations. I have about 5 minutes, I guess, okay. Or not? Okay. Not. Let's see. So the next run of LIGO Virgo is expected to start early next year. A long gap between 03 and 04 is becoming more and more disturbing. We are going to have much smaller sky areas. With 04, the median BNS localization is going to be around 33 square degrees, again, hopefully leading to more efficient follow-up. And there are plans of advanced upgrades to A+ sensitivities when LIGO India is also expected to join. And further down the line, detectors such as the Einstein telescope and Cosmic Explorer are planned, and these detectors are practically going to see all binary black holes or all stellar mass binary black holes which can be observed. For dark standard Sirens, there is a bit more to exploit, and this is cross correlations beyond line of sight contribution. So as I said earlier, if one looks at the distance and the redshift distributions and one changes the cosmology, at some cosmology, the fingerprint in the distance distribution is exactly going to match the fingerprint in the redshift distribution, giving us information not from just line of sight correlations, but from beyond the line of sight, effectively making use of gravitational wave sources, not as standard Sirens, but also as standard rulers. And two groups are following this up are thoroughly following up the prospects of this method. If we're looking years down the line, then current tensions in cosmology may have been resolved, will probably have been resolved, but standard Sirens will still remain the direct probe of h of z. So one is still going to measure directly h at whatever redshift or distance we are observing the gravitational wave source, as opposed to using calibrated distance indicator. So one can potentially measure other cosmological parameters such as the dark energy fraction, the matter fraction, or the dark energy equation of state, or even parameters beyond GR such as modified gravity parameters that affect gravitational wave propagation. On the other hand, one can also probe gravitational wave bias. Essentially, we heard about bias or galaxy bias in some of the other talks. This is very similar, but this would be how the gravitational wave source distribution is correlated with the underlying dark matter distribution, and essentially how this factor itself, how this bias itself changes with redshift, changes with direction, changes with masses which we are observing. One can also, because these third generation of detectors give us sky areas of less than a square degree, one can think of probing the universe with gravitational wave observations alone, not using cross correlations. And some authors have shown that we are already able to resolve the BAO peak with 3G gravitational wave observations. However, with 3G, we are going to have a different set of challenges. We are going to have so many signals that we are going to run into data analysis challenges. We are going to have very long signals and overlapping, which would overlap with each other, and this really needs some rethinking in the way we do our current data analysis. This is my last slide, sorry for going a bit over time. And this shows the various bands in which we observe gravitational waves. Here's a frequency. This is the current LIGO-Virgo sensitivity, the sensitivity of the Einstein telescope or Cosmic Explorer, which is very similar. However, we are going to observe, we are hopefully going to have also space-based interferometers such as LISA, which are going to observe in a millihertz band, and there are also other methods, completely different methods of observing gravitational waves, not by interferometers, but by looking at pulsars and seeing how these pulsars are slowed down or sped up as the gravitational waves are passing through them, the international with pulsar timing arrays, and with this wide range of detectors, the prospects of science in general and cosmology in particular with gravitational waves is very exciting. I'd like to thank you for your attention.
Hi, thanks for the talk. So how, as you get more accuracy and the signals, you can watch them for a longer period of time, do they ever get long enough that it actually helps you pinpointing where it's coming from and improving the accuracy of the angular determination? Because once you start to look at it in different angles from the same interferometer, then I guess I would imagine that you start pinpointing better that source. So it's not so much what is the instantaneous pinpointing that matters, but this for a long signal, that's a different calculation, or is it never long enough that this really counts?
So for LISA, that is absolutely true. So for LISA, you're observing signals for so long that you have essentially seen it from various different angles. But for 3G detectors, we are not there yet. I mean, they are long, but not, we of course do better because we observe it from different orientations, so that definitely improves, but not to the extent of LISA. I hope this answers your question.
But if they last so long that the Earth's movement,
so essentially the Earth is moving, so the detectors themselves are moving. So as the detectors are moving, you are observing the system from different angles, you are probing different polarizations, and this improves essentially the whole of parameter estimation of the signals.
So you talk about
let me just point out, I mean, the thing is, for ET, the signals are long in the sense it goes on to minutes, from minutes to hours, but not usually not days or years, which is. Yeah.
So you were talking about when you have several redshift possibilities for one luminosity distance estimate, and so you get an H0 with several peaks. How I didn't understand how you combine these H0 estimates to give a.
Okay, so by the way, this is only a cartoon. It's in practice, as you saw from the real results, even with one observation, you do not see a clear multiple peaks. You just see a vague underlying redshift imprint of the underlying redshift distribution. The idea is that for all these peaks, okay, for this observation, one of the peaks is coming from a correct association, the other peaks are coming from random associations. If it is coming from the correct association, then it is going to be at the correct value of H0, whatever it is, right? So this peak at the correct location will be located at 70 kilometers per second per megaparsec. This peak at the correct location will be 70 kilometers per second per megaparsec. So at 70 kilometers per second per megaparsec, you would always see a peak, while the other peaks would be at random locations. They would be there in some of these, they would not be there in some of the others.
So you take a difference between the.
No, you combine by multiplying all these together. Okay, that's how you combine likelihood. So you use the posterior of the previous experiment, posterior coming from the previous experiment as the prior for the next experiment. So you essentially end up multiplying all the likelihoods. So you multiply all these distributions, then the peak at the right location would get enhanced, while the peaks at the other locations would get suppressed. So this is a very simplistic cartoon, but we have also done some simulations which go beyond the simplistic cartoon, and we have also demonstrated that this works even when we have not 5 but 500 galaxies in the patch.
Okay, so can you go to slide 33?
Yeah.
No, sorry. I think it is the one that you have the error bars for the H0 from Cepheids and
this one?
No, it's way. Okay, but I think I can do the.
Oh, was it 34?
Yeah, maybe.
This one?
Yes, yes.
Okay.
So if I'm not mistaken, you said that the blue error bar falls with 1 over the square root of the number of detections, right?
Yeah.
So given the current rhythm of detections with electromagnetic counterparts, how much time do you think it will be necessary for you to... Okay,
Ricardo just left. And yesterday I had a bet with Ricardo that by 2032...
I was present.
Ah, you were present. by 2032, we will see bright standard. We will see bright standard sirens, and Ricardo said that we will not see bright standard sirens. I know that Luis here says we will not see 50 bright standard sirens. I don't know. It's but definitely very unclear at this stage. It depends on a number of things. It depends on the rate at which we observe the binary neutron stars.
But sure assuming the current rate.
Okay, we have observed one neutron star, essentially two more or less clear binary neutron stars, right? So it's a very low number statistics at the moment. So it depends not only on the rate of neutron star mergers, it also depends on how rapidly we can follow them up. Given the sky areas, okay, the sky patches are going to improve. Then there are other considerations also. How many of these would have bright counterparts? I mean, if you observe neutron star mergers even at 300 megaparsecs, you would not be able to see an optical counterpart. The counterpart itself may be intrinsically dim. For example, for the heavy neutron star, which I talked about, there's a possibility that there was a counterpart, but it was so dim that it couldn't have been followed up. For heavy systems which collapse promptly into a black hole, the counterpart is expected to be dim. So because of these considerations, it becomes very difficult to promise a certain number of bright detections.
So can I have, okay, it's the last one. You talk about sources that have electromagnetic signals as a counterpart. Could you talk about sources in which you have electromagnetic signals as a counterpart?
Yeah.
For the estimation of H0?
Yeah.
Can you have sources with other kinds of signals that can be used as counterparts?
Like neutrinos?
Yes, for example.
It would be okay. It would be reasonably difficult because the neutrino energies are quite difficult to predict. It would not come with a sharp energy, right? So the only thing that you can see for neutrinos is the energy, and I do not see very strong prospects of using neutrinos as distance or redshift indicators.
Okay, thank you.
Hi, thank you for the presentation. I would like to ask what would be the implications of the gravitational standard Sirens measurements of the Hubble constant converging for each of the two current measurements, the Cepheids or the CMB, or even a third value of the...
So you were saying, your question is what would happen if we end up agreeing with the Planck measurement, and what would be the implication if we agree with the Planck measurement, and what would be implication if we have to agree with the...
Or even a different value of these two.
That would be even more exciting. Okay. So the thing is, if we agree with the Planck measurement, then that would probably signal that there is some... I mentioned it in my other plot. Yeah. So if we agree with the Planck measurement, then that would signal that there is probably some problem with the calibration of the supernova results. I mean, this is also particularly, many of you would know better than me about this. This would could be because there are many steps in calibration which go in here. So if everything else agrees with this and supernova measurements stand out, there's some problem with the calibration on this side. While if we agree with the supernova measurement, so that means that all the local measurements agree, while all the measurements or the measurements from the early universe, they disagree with the local measurements. And a cosmological model has gone into obtaining H0 Hubble parameter in the current epoch from the early universe. So if we agree with the supernova measurements, that would signal that a problem with the cosmological model, the lambda CDM model.
Questions? I do have a question. So with the third generation detectors, we're going to see a lot of events. So at which point, so how often, because if there are many events at the same time and they're faint, they become background at some point, gravitational wave background, right? Or yeah. We'll always be able to distinguish and detect single events?
No, so the idea is these events would be in the foreground, so one would see a coherent signal from these events.
But could it be like you have tens of events at the same time and they cannot distinguish between them, or you'll always be able to?
Sorry, where was I? No. It's one is not looking at many. One is not looking at order of 100 events at the same time. So of the fact 2 or 3 events at the same time, and one would be able to distinguish between them because one important thing is even if they're in the same, all in the band in the same time, they're merging at different times, right? So there you see a very clear signal from the merger. So the searches would very clearly tell you this is where one event is. Then you can essentially use that information and you can in some sense try to take that bit out, use the merger and then take that bit out. You're left with the residual with the rest of the signal and do a parametric inference for the other signal when it's merging. So this is essentially what helps us.
Okay. Other questions?
It's on a comment. In that plot that you show the signal-to-noise ratio, passing the template around the output of your detector, if you have a lot of signals over there, you could see a lot of peaks in the signal-to-noise ratio.
Yeah.
And this could be used to distinguish many different signals that you have in the output of your detector. Suppose you have 2 gravitational waves passing your output of your detector, and you will see 2 peaks of the signal-to-noise ratio. Yes?
Yeah.
Could be used, yeah.
Yeah. So that's what I meant. So the thing is, the search itself would show all the interesting would show all the mergers. Yeah.
Okay, so we close here. So thank you again.
Which far did I go?
Very good. So we've got Sirens. Suppose I have dark
Hello, good afternoon. Let's start the colloquium. It's 4 past, I think we can start. So it's a pleasure to have here today Lehner from Parametric Institute from Canada. As you know, whenever there is a workshop at ICTP, so we kindly ask one of the person involved in the workshop to give the colloquium. So the workshop on application of gravity just ended, and actually we'll end with this colloquium. So there was the handing of the PhD prize in gravity, and it makes sense that it's Louis to wrap up this activity. So Louis is not a guest here. I mean, he has from Parametric Institute, he has many ties with ICTP, many common activities. And so he's part also of the board of ICTP, so he's really part of this community. So he started his undergraduate studies in Cordoba in Argentina, but he soon moved to the United States for the PhD in Pittsburgh. Then after a series of postdoc in North America, he first landed in Louisiana and then to his present position. Among other things, he's one of the 10 most influential Hispanic Canadian people, so bear this in mind. and of course, he's active in the area of gravity, gravitational waves, all aspects of theoretical and phenomenological gravity. And he's an expert in strong gravity. You might think it's a contradiction, but it's not. Strong gravity is a subject of huge amount of investigation nowadays. And in particular, today, the main focus of his talk, it will be some applications of the recent detection of gravitational waves to the structure of black holes, one of the most fundamental objects in nature that we know. So, Louis, please.
Thank you, and thanks for everyone for coming. Thanks for that introduction. It's always a pleasure to come to Sao Paulo in particular, ICTP-SAIFR. So I'm from Argentina. Every time I step foot in South America, I feel like I'm home. Okay, so you might wonder, why do I have some striped animals there? There's a point, and I'll try to make it as I go through my talk. So I'm not sure if you heard the story of this legend that Pablo Escobar had a big farm in Colombia, where he had lots of African animals, in particular zebras. But the legend is that at some point, the zebras were not there because they hadn't arrived, and he wanted to impress some of the guests, and so they grabbed donkeys and they painted stripes. These are not those zebras, because that's a legend. These are real donkeys that were painted in a zoo somewhere. I'm not going to say the country, it doesn't matter, but the point is you can do a pretty darn good job making a donkey look like a zebra. And yesterday we had a really nice talk by Raul, who in the second part was talking about machine learning and their ability to discern things given some score. I wonder how well one of these machine learning techniques, what would be the score of thinking that this is a zebra? You don't think it would be good? You think it would tell them apart? Okay. So anyway, so this is part of, you're just going to see as I go through my talk why I bring this up. There is a little bit of a controversy going on, which will gain some steam till we actually resolve it. You might think that it's a lot ado about nothing, but there is a lot riding on this. So hopefully I'll go through this in a clear manner. So I also need to say something, or I start with a caveat for my talk. For the past few years, we have been testing this new way of doing seminars in group meetings at Parametric Institute, where we ask the speaker, come with a punchline. Your talk is only 10 minutes long, and the audience will drive their next hour. So I'm doing a sort of hybrid here. I don't have a lot of slides. Please interrupt me at any moment. I can go on a tangent and talk about anything that is related to what I'm going to be saying, and I will just move around quite a bit. So by all means, please keep this interactive if you can, or if you will. We find this mode of doing seminars quite useful because it actually is very conducive to especially young students asking questions. if they don't, typically students tend to be shy because they're afraid of opening their mouth, asking a question because, oh, maybe I should know about this. Well, but if the speaker is not telling you everything, you have plenty of excuses. You're not supposed to understand everything, so you ask questions. And so in our experience, this has been pretty good at engaging students, especially in the time of COVID. Okay, so what's the setup? So of course, as you know very well, we're in the era of gravitational wave astronomy. It got started in earnest a few years ago, 7 years ago, with the first gravitational wave detection, the first direct gravitational wave detection. And now, kind of all windows are open to ask many questions in many fronts, and I'll talk a little bit about some of them, and then I will home in a very particular point or a very particular topic that, as I said, has become a little bit controversial in the past few months. So, I mean, underlying everything we do in astrophysics, cosmology, even particle physics nowadays, is this famous equation by Einstein, an equation that Ricardo has told his students during his class. So on the left-hand side, we have the Einstein tensor, and on the right-hand side, we have two contributions, one given by the matter content, and the other one given by the cosmological constant. And we know this embarrassing reality that about 75% of the energy and matter in the universe, we don't have a clue what it is. It's dark something, either matter or energy. And okay, we shoved quite a bit in there, like we have 75% in there, or 70-something is in there. And there are 20%, it's dark matter, which maybe is somewhere there. But there are quite a bit of efforts to try and say, well, maybe this is not, it's the left-hand side that will have to be changed. It's not a Riemann tensor, it's something else that is kind of describing gravity in a slightly different way, not as this dictated by Einstein's theory of relativity. And then we're trying to, in more than one way, explore what gives. So the type of kind of test that we have been going community-wide to try and test general relativity range in many aspects and through many years. But two particularly interesting numbers, or combination of numbers, is the following. So in the horizontal axis is essentially the gravitational potential of typical sources, or the gravitational potentials that different experiments are targeting. And here is, you say, well, given a source that has some amount of mass m and some characteristic size L, the m over L is telling you how strong the gravitational potential of that object or that region is. And if you move all the way to order 1, this is where black holes sit. The other axis is the curvature axis that basically tells us how strongly curved within this picture of general relativity the space-time is and what is an associated length scale to it. And okay, we go from very small values to, again, order 1. And for going here, order 1 in both directions, we're talking about black holes that are quite small. So gravitational wave detections targeted by Earth-based detectors so far are kind of probing this region. The Event Horizon Telescope, which is probing the vicinity of a supermassive black hole, covers through this region. So even though it's reaching potentials that are of order 1, of course, every time you talk of a black hole, you're sitting somewhere here. But because it's targeting supermassive black holes, the scale is much smaller. And of course, then we have done quite a bit, or the community has done quite a bit through pulsar timing and pulsar measurements. And this goes quite a bit there, doesn't quite go all the way up as gravitational waves, but for a number of sources, it's quite competitive to what gravitational wave detectors on Earth-based detectors we can get. And with that, a significant number of constraints on potential deviations from gravity has been put forward. But of course, the most exciting regime is right here, when you try and push in the most extreme regime. And this is part of what I'm going to be trying to talk today and related to that controversy. Just to put things a little bit in perspective about what's happening and what's coming. So far, we have detected gravitational waves directly through ground-based interferometers. And these are targeting black holes or neutron stars, objects that have between, say, a few solar masses to 100 solar masses. This is the range in frequencies that you can reach. Space-based interferometers, of which LISA is better known, but there is a Chinese one that is also kind of gathering quite a bit of steam, and hopefully they will be up sometime in the future. So this is targeting the end of the 2030s detectors. They are targeting smaller, lower frequencies because the frequencies of gravitational wave decay or goes inversely with the total mass of the system. So their main targets are supermassive binary black hole mergers in particular. If we keep going down in frequencies, what we can do with pulsar timing arrays, so the idea is you detect the pulses coming from a collection of pulsars, and if there is any delay or change in the period between pulses, maybe a gravitational wave went through, and this set of collaborations, there are actually 3, maybe 4, are collaborating nowadays, and there is all the expectation that sometime in the near future, maybe next year, they will come out with some announcement, perhaps constraining the potential background of gravitational waves of supermassive binary black holes that are far from colliding, but are producing gravitational waves nevertheless, and their collective signal would hopefully provide a background to these detectors. And if that signal is not there, well, maybe there is further indications of this last parsec problem, which is this very famous problem in astrophysics, where if you imagine 2 galaxies coming together, each galaxy having a black hole, it's hard from theoretical considerations to find out how these 2 black holes will come together in a time that is less than the Hubble time, unless you invoke some very interesting mechanisms to accelerate the merger history when they are pretty far apart. And another, this is not direct detection of gravitational waves, but it's indirect, which comes from primordial gravitational waves that get themselves imprinted in the CMB. There was a claim some years ago that then was retracted, but detections are getting sufficiently accurate that hopefully we'll get to hear something in the next few years about that. So just one slide on this, and if you want more details, please ask, or you can, I also strongly suggest you take a look at Archisman talk earlier today, which was beautifully explaining some of the techniques that gravitational wave detector detection use today and what's involved. But typically, there are some exceptions. Typically, what gravitational wave detectors do today is they're trying to get gravitational waves that are very buried in the detector's noise. So a typical detection of in LIGO, Virgo, and Kagra these days is kind of like this. You have noise, and very deeply hidden in it, a gravitational wave is to be found if you do the right job. So what's the task to do that? Well, you need a set of templates, something to help you go search in the haystack for that needle. You create gravitational waves for all possible things you can imagine might exist, and then you go through the noise, and then you do this so-called match filtering. So you go one template after another through every single chunk of data that you have, and if there is a coincidence, then you dig the signal out of the noise, and that best match not only tells you just detected gravitational waves, but more importantly, is telling you what the parameters of the source are, and with that, you start doing astrophysics. So in particular, you extract the masses of the systems that are coming together, their spin, and their distance. So all that intrinsically is a major piece of information for astrophysics. So one of the greatest promises of gravitational wave detection was, I always teach my particle physicist friend that, well, you're going after the Higgs back before they detected. But if you get it, only 50% of the chance will be an exciting result, because you either find it where you thought it should be, and so what did you learn? Nothing. Or it was somewhere else, in which case it's pointing to new physics, and that would be exciting. For gravitational waves, we had the luxury of either way, it's great. If it misses general relativity, you have something new to do. If it's exactly as expected in general relativity, you're doing astrophysics, which again is something new, and we are seeing both playing out nowadays. Eventually, the better detectors are coming online. The ones I mentioned on space would have a signal to noise, or a noise level, if you want, much reduced when compared to the gravitational wave signal. And there are third-generation detectors that will come in the 2040s, where in reality the signal will be much louder when seen in those detectors, and the noise will introduce a jiggle, which of course will not prevent you from seeing the waveform, but you still will need to do this match filtering to get a good information of what the best match to the signal is so that you can do physics. Of course, the techniques is expensive. You need to create the templates. There's major work on the theoretical front to create those templates. And for instance, Ricardo leads one front in trying to understand the early part of the signal. I'll say a few more things about it in a second. But once you have the templates, you need to encode that information in an efficient way so that it can go and then perform the analysis. You might have gazillion templates that then you have to go and beat against the noise every single time to try and find which one is the one that has the best match. And once you have all that, well, on the gravitational wave plate, you can do astrophysics, you can do particle physics, you can do cosmology, you can do fundamental gravity. My talk is going to be mainly covering this point, or one particular question along this line. But here, there's already plenty of very interesting features that have been understood. And just to mention a few examples, for instance, in the context of astrophysics, by now, gravitational wave detectors have measured about 100 binary black hole mergers. Those binary black hole mergers have informed the population. We went from not having direct evidence of any black hole out there to having now 100. We now have the distribution of their masses, both in the mass parameter, but also in the distance. And it's already kind of giving some hints of some interesting features. For instance, some of the black holes that are the most massive that have been found are already pushing on theoretical ideas from astrophysics front that thought there was a very hard limit to the most massive black hole you could form, which was about 55 solar masses, before something will prevent that black holes between 55 and above 100 to form. Now you go with gravitational waves, you have something that is 65, it's already pushing on these astrophysical models. There were also, this was called the upper mass, or it's called the upper mass gap. In the distribution, there seemed to be also an overabundance around some masses of black holes. Still, this has to be firmed out. But if that's true, it's hinting of a possible different channel of formation, and maybe some of those are black holes of primordial origin, which will have something to say about the dark matter models in the universe, for our universe. There is also pushing back on something called the low mass gap. It was believed, primarily driven by observations, that there shouldn't be black holes with masses lower than 5 solar masses. Yet LIGO has already observed objects of 2.6, 2.9, or thereabouts. So either you're finding the most massive neutron stars in the universe or the lightest black holes from astrophysical origin. And again, this is giving a lot of food for thought for astrophysics. In particle physics, there are very interesting models, say, to explain dark matter, one of them being the axions. And axions are some massive fields that, when interacting with a black hole, can lower the spin of a black hole in a significant manner. So by scanning the possible set of angular momentum that black holes are observing, you can put constraints on that particular dark matter model. In cosmology, we're seeing the very early efforts that using, and this is something that Archisman also discussed in his talk very beautifully, provide an independent way of measuring the Hubble constant. Of course, it's still not competitive because the errors or the potential width of values is still too broad to be fundamental in cosmology, but it's something that will only get better as more signals are detected. So that was just a little bit of a hint or a glimpse of some of the activities that are going on. But for the purpose of my talk, I'll be thinking mainly on, well, how can we then use this information to detect or to test general relativity and some of the problems that we have to face in there. So as I said, well, with gravitational waves today, we're extracting physical parameters, understanding the sources. We are struggling and working hard at encoding very efficiently the gravitational waves, but typically, let's say gravitational waves are looking like this. So there's an Erlang spiral where these objects are going around each other. The good description for them is can be obtained with post-Newtonian expansions. So expansions are rely on the fact that the velocities are low and the orbital frequency is low, and you can rewrite these equations in a way that mimics Newtonian relativity with several correcting terms, and it's harder and harder to compute further corrections, and this is one of the things that Ricardo does, but you're actually getting a better and better description of the early part. At the late part, you assume, and there's something that was called the ultimate state conjecture, that is, it's a conjecture, I'll say a few more things later, that says that the ultimate object that you form when there is a collapse in the universe is a black hole. And that black hole is described by something called the Kerr solution, and we'll get more into that in a second. But that gives you a recipe to obtain a pretty reasonable description, and how reasonable is the key of this talk, for the after merger. And in between, you have to use numerical simulations, put everything together, and encode that information. But what does it really mean to test generativity? Well, at the very basic level, you can do a null test of GR. So if you know everything that you should expect in generativity, you go to your signal, you test, and you say, is it sufficiently consistent with it that I can discard a hypothesis that it's not generativity? So the outcome is two. Either you're consistent with generativity to within some tolerance, or you're not. So far, every single test says you are consistent with generativity. But if the test were to say it's not, even that null test that will say, no, it's not described by generativity, doesn't tell you yet what is the thing that is replacing it. So for that, you need better tests. So there are tests that are called parameterized tests, where you go to your signal, and short of knowing what a putative best alternative solution should be, you modify ever so slightly the parameters away from the ones preferred by generativity, and you ask the question, is there a preference for this value to be off from the value from generativity? This is what the LIGO scientific collaboration is doing nowadays very, very deeply. There are others that say, well, just take the best match from generativity, you subtract it from the signal, and you ask the question, is there anything left? Is there a residual that it can make sense of? And again, these are tests that are being done, pursued nowadays. And with in very few exceptions, when you can't compute signals beyond generativity, and I'll tell you why later on in the talk, this information is being used to further refine these tests. So it is complicated, but depending on what regime you're actually looking at, there might be some clean stages where you can say, well, maybe here I have the best chance of testing GR in a very strong way. So what's that state? Well, first is the observation. You just look at this and superpose is the result from numerical relativity, so for the full general relativity thing. And you say this is so simple looking on one hand. So it's just sinusoidals. They go up a little bit in amplitude, go up in frequency, and then it decays. Then maybe GR is doing quite a good job. Waveforms are very simple looking. Maybe there are some simple arguments we can use to efficiently encode this information, efficiently go after what potential deviations would be. And this is pretty much the name of the game. And it's awfully tempting to say, by looking at the waveforms, that the system is behaving so smoothly, so kind of uninteresting in some ways, not showing any craziness here, that the system is behaving essentially linear. This is in between big quotes. Because it's obviously not linear. It's not the fact that you can add two solutions and you'll get a third solution. But it's just this kind of bad terminology to say there aren't surprises here. I don't see anything crazy going on. It's a smooth sweep up in frequency. It's a smooth sweep up in velocity. At some point, a common horizon forms and the system decays. So we're going to get more into that. So let me just take a step back, put all of us in the same footing as to what things we're going to use for the test that we're going to carry forward. So general relativity was this very complicated theory. People struggled with it for a very long time, even early on doubting about the reality of gravitational waves. Even Einstein himself, the paper he sent for publication was basically saying gravitational waves are not real. It was a referee, the one that corrected them, and the paper got changed on the proofs from the non-existence of gravitational waves to the existence of gravitational waves. So, but some gold in all this that Match is writing on are these observations. For instance, well, black holes are this one-way membrane in solutions of the theory, where at the classical level, information can only go in one direction, nothing can come out. And associated to that, we have this cosmic censorship conjecture that says every singularity that might be in nature is hidden by this horizon, and therefore we don't have to worry that classical physics is breaking down. We can do physics safely outside. Then we have some very basic black hole solutions. The one that we think is astrophysically relevant is known as a curved black hole that is described by 3 parameters: mass, angular momentum, and potentially charged, but astrophysically we believe they should be neutral, so only 2 parameters govern them. This is a solution that is extremely special, and we use it so much that sometimes it gets lost how special this solution is and how brave must one be to rely on it so strongly. The solution is found by assuming axis symmetry and stationarity. So 2 very, very, very special conditions. So, I usually do this example. If I assume stationarity, I can imagine a pen standing on its tip is a solution. But of course, no one expects to enter a room and finding a pen standing on its tip. For that, we need to find out where the solution is stable. This is something that later on was tackled, and I'll say more about that in a second. But associated to a curved black hole, we have some very key kind of concepts. One is that there is the so-called innermost tabular circular orbit for particles, for test particles. So just as in Newtonian mechanics, we know we can set up binary systems that have stable circular orbits and it will go on forever. In general relativity, that's not the case. For test particles, we can do it up to a point. From some radius inwards, no circular orbits exist that are stable. So just anything there within this innermost state of circular orbit, things will just fall in and have a merger. A similar concept exists for massless fields or massless particles, which is a so-called photosphere. And there's also something called the Anergosphere, which is this region very close to the black hole where things are dragged in such a way that you can tap energy from the black hole that is rotating and transfer that energy, if you want, to fields or to particles. And so things like superradiance or black hole jets are tied to this ability to extract energy from a rotating black hole. And the last kind of foundation that we can get from here is that there is the area law for black holes, that the area of a black hole never decreases. In every interaction, the area grows. Even when you take energy away, the area is growing. So here I'm going to the controversy. The controversy is related to the following claim. And the following claim is gravitational waves have already allowed for black hole spectroscopy. And I'll say a few more words about this in a bit. Essentially, you have measured enough properties of a black hole to put a very, very stringent test on, if you want, the multiple moments of a black hole, which in general relativity say, if you measure one of them, you immediately know all of them. This is not true in other theories. So the claim is that with the current data, we have already seen more than one. Of course, the results so far observed are consistent with GR, so this is a freakingly strong test of the theory. And worse yet, or more important, or stronger yet if you want, you can do this in such a way that even you can push all the knowledge that you have, that you know in the linear regime, all the way up to the merger epoch. So already from the moment where two black holes become one, you can do a linearized approximation to describe the system. This is a really bold claim. And we'll go on through the evidence. So this is a claim by EC and FAR, but Carullo and collaborators and others are pushing back. This is with respect to the data. With respect to theory, you can also do that, and we're going to go through the analysis in a bit. These are claimed by Gisler and Tucholsky, and this is a very strong collaboration, and some authors here are from the same first line. So EC is a co-author here. But of course, there are others that are pushing back, and Ota describing her talk, their ideas on this. So let me review a little bit of the evidence, and then we're going to go back. So I'm actually playing like a role of a district attorney, and I'm pushing back on this claim. This is my bias, and I'll tell you why. So imagine you have a black hole. Remember I told you we had this Kerr solution, and we are using it as a foundation to describe a black hole accreting. The EHT collaboration published image of a black hole using intrinsically that the Kerr solution is stable. So how do we know that the Kerr solution is stable? Well, we know it for the following reason. You can take perturbations of a Kerr, and if those perturbations are massless, that's an important caveat, what you find is all those perturbations decay exponentially. And they decay with kind of an oscillation frequency and a decay frequency, and if you combine this, the decay rate and the oscillation, you obtain out of that the mass and spin of the black hole. And any mode that you can think of, say described by different L and M modes, they all give you the same information in general relativity. So what is this a little bit more in details? Well, you assume that your solution is described as the solution for the Kerr black hole plus a small perturbation. You put this into Einstein's equation at the linear level, so you assume a linear approximation is good. And then you ask, what is the behavior of solutions that have this shape, some exponential to some I omega t, and this omega could be is complex, so it has both a real and imaginary part. So a real part will describe these oscillations, and the imaginary part, if it has a right sign, will have the decay. If you find any evidence of the wrong side, you're going to have an exponential blow-up, and you don't find that. You always find an exponential decay for massless perturbations. So, of course, these modes, you can say, well, it could be labeled by L, the angular momentum number, an azimuthal number. When you plug in, you find more than one solution for a fixed set or for a fixed value of L and M, and this N is overtones. So these are the further solutions you can have for fixed L and M. So this is some plot that shows like the real part in the left-hand side, and this is a Q, so it's the inverse of this omega. So it just basically says how quickly the system is decaying away to zero. And depending on what values of L and M you pick, they decay faster and faster. So the higher the L, the faster the signal is going to decay. So when you collide two black holes, you expect that the fundamental mode, the one that is the strongest in general, will be given by the L equal 2. And associated to that, you're going to have different frequencies. And of course, in the right-hand side, in the horizontal axis, what you have is the angular momentum. This is A, the parameter A. There's 0 for a non-rotating black hole. 1 is for the maximum rotating black hole.
So you just use the word colliding black hole. You say that's a linear perturbation, colliding black hole?
No, okay. Great, but that's exactly where I'm trying to go after. So after the black hole mergers, you first solve the problem in full. You take numerical relativity, say, and you see in full, and you see a waveform that looks like that. A few oscillation, it goes up and down. Then you say, well, can I rely? So I see that if I wait long enough, the system decays to zero. So there is a regime here that maybe a good description with respect to a Kerr solution exists. Not only that, you say, well, if a good solution with respect to a Kerr black hole, the Kerr black hole being a good approximation to the solution here should be good, it would be consistent if the mass and spin I measure here are the mass and spin I can predict I would form from the individual parameters of the system early on. And you keep seeing this consistency. And this goes to this ultimate state conjecture, a conjecture by Israel and Penrose, that said, well, if you wait long enough, a collapse scenario will give rise to a Kerr black hole. And it seems that you don't have to wait that long before a Kerr black hole with some small perturbation is a good approximation. So, but thanks for that. Yeah, so here what you're saying, well, the outcome of a merger, that's an assumption that is supported by first the numerical simulations and then what you see in nature in gravitational waves. There is a, if you wait sufficiently long after the merger, a good description should be possible using this terminology. And then the question is how many of these I need? Maybe I need many of these modes to do a good description, and this is part of this controversy or what underlies this controversy. Let me just make one observation before I move on. So take the L2, the M2, I told you these are the fundamentals. These are the ones you believe will have the strongest content in general. And let's consider the slowest decay in overtone, the next slowest, and the next to next slowest. First, let's look at the frequencies, the real frequencies, the oscillatory frequencies. In whatever units of M, this is, let's say, the 0.53 is the fundamental one, 0.52 is the next one, and 0.5 is the next one. So these are three oscillatory modes that have almost the same frequency. So they are ringing at about the same frequency. But the decay rate is significantly different. So it's 0.08, 0.24, and 0.40y. So this one dies much, much quicker than that one. This one dies off much, much quicker than that one. OK, let me review. I'll get back to this in a second. But let me review first that claim, the first claim. At the theoretical level, we can use linearized perturbation theory, this is the claim, to describe the behavior of this decay of a black hole almost all the way to the merger itself. So what did they do? You take a numerical simulation that has been specifically tailored to be extremely accurate. So it's the most, let's say, the most accurate waveform you can get. You get the waveform, say that waveform, and you say, I'm going to insist on trying to see if I can fit that waveform using simply the linear analysis. And then you ask, well, if I use only, and I'm going to insist also only of using L2, M2. I'm going to put one over the fundamental overtone, and as many as I need, and ask the question, can I get a better and better fit to the data obtained numerically at the theoretical level? So if you put the first overtone, that's a signal. So here what you're measuring is a signal that you have obtained analytically, well, numerically, with using general relativity and a numerical code, minus a signal that is just, let's say, first, just A0 e to the I, let's say, omega 0. By that I mean L2, M2, and N0. So I said, I want to fit with this. Can I do a good fit? And then you say, well, I have my true waveform. I do the inner product with my test waveform. Oops. And then I get a figure of merit out of here. I say, how good is this? So I can do 1 minus this one, let's say. If this were exactly equal to that one, I would get a 0. And that 0 will be the mismatch. And anything that is away from 0 would be the error I'm making in thinking that this is a true waveform when in reality it was that one. So that's for 0. Then you can say, well, let me put 0 and 1. That's that one. 0, 1, and 2, that's that one. And the more you actually put, they go all the way to 7, not only do you get a better match, but you also can push earlier and earlier and earlier to have a better fit, all the way to 0. And so that's the claim. The claim is you can go almost up to the point where these two objects got to merger. By that you mean the highest peak in the waveform. From there on, it seems that a good match is obtained by simply using a model that relies on just a linearized analysis. So you have sum from n equal 0 to 7 of an omega n. and just using the fundamental overtone. Of course, this is a merger of two equal mass black holes that are non-spinning. So that, let's put that on the side. That's evidence number one. Evidence number two is the experiment. You go to the data, you go to the loudest event, which was the first one, GW150914, and you do the same analysis, but with the data. You insist of just using this, and this is the H detected. And the claim is that the evidence favors having not just the zero mode, the zero overtone, but also favors having one and potentially having two. So the claim is that you do a better job fitting the data if you use more than one overtone. Not only that, there is a practical implication, because if you use just the zeroth mode, the zeroth overtone, you would predict that your signal or your parameters are consistent with this this ellipse here. But if you add one or two, you shrink it and you move it around this point, and this is the point you knew the answer should get, because from the earlier in-spiral regime, you could detect, you could draw what the masses should be, and from there, using a lot of theoretical analysis, relying on numerical simulations, you can predict what the final mass and final spin of the black hole. So the claim is if you only use the zeroth overtone, you don't get a better, a reasonably good fit. You can do a much better fit if you include the overtones. So it seems that the evidence here is uncontroversial. We should be very happy. You can do a much better match. You can get more than one overtone. And with that, you can even begin to write or be calling an agency to buy your ticket to Sweden. Because this would be amazing. It would be not only the detection of gravitational wave, but the spectroscopy. Yes?
Sorry, I don't understand what the claim is.
Okay, the claim is here that, let me put it this way. Each one of these omegas are independent. So each omega, it depends on the mass and the spin of the black hole. Measuring only one of them, because you actually have two pieces of information, the real and imaginary part, you can get the mass and the spin out of this. And if you measure two that are independent, 1 and 2, you can have a very, very strict constraint on what, if you want, out of this you get the mass and spin, you predict which one this should be, and that's what you get it. So the claim is that in the data, if you analyze it, you get not only the fundamental overtone, but you get at least the first one that comes after one.
The omega is complex, it's two parameters.
Yeah, that's what I said. So this one, you can get two equations out of this. You get the mass and spin. With this one, you can predict which this one should be, and that's what you're getting. So that's a claim, that the data already favors a model with that. But that claim, okay, the moment you buy this, you're beginning to buy further other things, which is what I'm trying to push back on. So the claim, the overtones of a black hole have already been measured, at least two modes, the fundamental and the first overtone. So this gives you a black hole spectroscopy, two independent measurements, which has very strong evidence for GR, and of course, have practical consequences of the source identification. It gives you a better sense of what the parameters of the source will be. The results are obtained as in GR. People call this the no-hair theorem test. I don't like the terminology because no-hair is a statement for stationary black holes. These are not stationary black holes. This is a much stronger test. So I really dislike people using no-hair theorem test when they are doing much more than that, out of which one consequence is a no-hair. What they're doing is testing the ultimate state conjecture, that the system very quickly relaxes to a black hole given by Kerr. But not only that, already from the merger itself, the system is describable in linear terms of the Kerr solution. If that's true, well, that gives you very strong confidence in even the template construction that you need to do to efficiently encode information to go after signals. But if I keep going down rabbit hole, I don't see any way I can get out of the following claim. I just collided two objects that are of order 1. So I take one, I hit it with another one, and the system is behaving linearly? So what the heck? So this means that black holes do more than just high singularity. They also find a way to hide nonlinearities. And that is like a tall order for me. It's going to take me a long time to believe that. So I'm going to go around and say, well, can I have arguments that are strong to claim that we should be careful when we do this kind of analysis? OK, so first, this is where I'm going to start trying to push back a little bit. So let me first, well, recall where we come from and some of the potential problems associated with that. So any time we use any perturbation to study any system, we have some dangers. And since we've been using perturbation theory for such a long time, sometimes we forget about them. And this is perhaps the reason why I went into numerics, not on perturbations, because I always find that kind of iffy. So depending on the type of perturbative scheme I choose, I might hide some potential issues that for that I need to work out higher orders before I can understand it. And different strategies might give me different answers, and only through suitable resummations I can put everything in the same context. So let me give you a very specific example. Take Navier-Stokes for simplicity in the incompressible case, divergence-free. So the equations will be given essentially by this structure. The time derivative of velocity, then there's an addition of the nonlinear part, v dv, and the dissipation, some eta over rho, whatever, Laplacian of the velocity. So now you can choose your perturbative scheme. I tell you one, smallness of the velocity. So if I use smallness of the velocity, this term I keep, this term I throw away because it goes like velocity squared, and this term I keep. So all of a sudden, my equation tells me that velocity will decay exponentially with a rate given by n. So now what I've gotten is a solution that tells me all fluid description is laminar. I just have decay. My perturbations decay. Let me choose a different perturbation scheme, which is a perturbation scheme based on the gradients. I said derivatives are subleading to higher derivatives of the same field. So here I have a first order derivative. Here I have a first order derivative. Here I have a second order derivative. I throw this away, and I obtain the solution to this equation. When I do that, what I find is all modes are turbulent. So I recovered a turbulent regime, but I lost the laminar regime, and vice versa if I did the R1. Of course, we know better that if you compute the relationship between this and that and which one wins, we arrive at the famous Reynolds number in fluid dynamics, which tell us if you're below this one of the perturbation scheme is a suitable one. If you're above, the R1 is a suitable one. So we have to be very careful when we stop a linear and we don't know anything about the higher order. So in no particular order, I'm going to give you 3 arguments for what I think we should push back on people trying to buy a ticket to Sweden so quickly. So, and for that, I'm going to go here. I'm going to remember this quote by Ulam. And this is saying, well, using the term like nonlinear science, like referring to the bulk of zoology as the study of non-elephant animals. So what I claim is, well, linear perturbation is us studying elephants. There is a whole zoo of animals in the zoo or in nature that we have to be very careful before we dismiss them or not remember that they are there. So first, I need to make sure that I remember something. We sometimes, again, forget that we use 2 subtly different terms, sometimes interchangeable. Linear stability and stability are not necessarily the same. So linear stability means the solution to your full problem in the small regime, in some code, is the same as the solution to the linear problem in that small regime. That's not necessarily the case, always. And stability is just that the system decays and nothing weird happens. So the example is take your coffee and stir it. There's nothing that goes stable unless you're crazily and then just everything spills out. You just stir it a little bit. This problem there is definitely stable, but it's not linearly stable. You perturb with a given mode, and other modes will be created due to nonlinear interactions in the fluid. Of course, they might be very subtle, might be very small, might not be very obvious, but if you put your Fourier glasses, you will see these other modes being created. So what evidence do we have? And some of this is has been there for a long time, that nonlinearities are present, even in the merger of two black holes, from very, very early on. So one example was this. This is a work that was done back more than 20 years ago in the so-called closed limit approximation. Back then, we didn't have codes to collide binary black holes orbiting. The best we could do is just head-on. So people were doing head-on, and at some point, the same strategy was pursued. They said, well, at some point, these objects are coming so close that it should be able to describe, with perturbations over Schwarzschild. And perturbations were carried out to first and second order, so they could actually ask the question, if the merger takes place, how do I get a better fit if I use the first order or the first and the second order? And you can barely see it, but the true signal is a solid line. If you just use the first order, this is a dashed line. If you use the first and second, you do a better job. So it's already hinting that further stuff is there, and the linear perturbation, the linear analysis was not able to capture everything. Another thing that we did also a long time ago was to ask the question, I have a black hole, I'm going to imping it with some packet of gravitational waves, and I'm going to get the scatter signal. And if the problem were linear, the signal that gets scattered, if you divide it by the amplitude of what you throw in first, should always give you the same answer. And here these lines show that for a large value, large set of very small values, indeed, everything lines up on top of each other. But as you increase it, you got further and further structure that the linearized analysis would not have captured. So that's evidence number one. It was there. Evidence number two is what I said before. If you really want to rely on or understand or see how much you can rely on your first order theory or approximation, you should work out what the second order perturbation would be doing and then compare. So very recently, people have undertaken that. It's complicated for Curve, but there is a series of new works where you basically say, well, I already had solved, let's say, the linear problem, and the second order problem will have this solution act as a source for the second order. And you can, once you solve all that, you can show that for a perturbation that has, say, the H1 has this size, it induces a second order perturbation that, albeit small, it's there. So in the virtue of time, I'm going to be just basically going to the punchline in most cases, but tell you what the basic solution is. So some years ago, also in a very different context, this is related to ADS-CFT applications, we were asking about the quenching of a system, of a Hamiltonian, so where you had some object, the dual picture of the quenching problem was a black hole where you're going to hit it. And you're going to, the experiment was such that you could hit it in any way you want, ever so slowly, or just punching it with the same amount of energy, but with a very, very short time feature. So what you saw there is you had a black hole, you send a pulse. If this pulse was extremely long in duration, what you found is that, okay, you're in the adiabatic regime, and the space-time responds in a very much the same way. So if I put an L2 mode, I got an L2 mode coming back. And that was universal. At the other end, where you did it extremely fast, there was another universal regime, which was highly nonlinear. But when you ask, in the collision of black holes, what type of punching are you in? Are you in the very slow regime or in the very fast regime? And the answer is you're in neither place. You're in the middle. This time scale of the perturbation, if you want, is order m. The time scale of the decay of your black hole is to a Kerr black hole is order m. So you need to understand this in some better fashion. But deep inside, what they are doing when you think that after the black hole merge, let me go back here for simplicity. Imagine, let's go here. When you're here, if you're actually going to believe that from this peak of the waveform onwards, you can do a very clean decomposition using a linear analysis, what you have to remember is that each of these modes are modes of the black hole that has mass m and spin a. But as the process goes on, some of the energy falls into the black hole. We know by the area law that the black hole will change its mass ever so slightly, will change its spin ever so slightly, So now a pure mode for a black hole of mass m and spin a is no longer a pure mode for a black hole of mass m prime and a prime. So you would have a collection of new modes, which already says this is just too naive, because that frequency there that knows about mass and spin is changing because the mass and spins are changing. And so we have this result very recently that basically point out. And the last example I'm going to give goes back to the following as well. So a black hole that has some gravitational waves around. So I just formed this black hole. There is still gravitational waves around. These black holes are propagating. These gravitational waves are propagating. But as they propagate, they introduce some time dependence of the system. It sources slow, small changes on the spacetime themselves. And the equation that you should be considering is not that G, the metric is the metric of curve plus some perturbation. In reality, what you want to think is that the metric is some time-dependent metric, slowly varying because of the presence of that guy. Then you can ask the question, how does a perturbation behave if my spacetime is curve plus something that slowly is varying with respect to the space and time? And what you find is there is an instability, a parametric instability for some modes that says this energy in this mode will couple with whatever other very tiny, however small mode is, and will preferentially send its energy, or some of its energy, into those modes. So that calculation we did some years ago. It doesn't matter the details, but parametric instability is something that is taught in classical mechanics. Usually it works out when some conditions are met, and the conditions are here. It doesn't matter, this is a mouthful, but basically you're trying to make this thing the largest possible, which is the size of the perturbation divided by the azimuthal number and the decay of that mode itself. Okay, what does that mean? I'm going to do this exercise. Take that amplitude, and let's think in fluid terms. In fluid terms, the amplitude of the perturbation is my velocity. The 1 over the azimuthal number in fluid terms is like a wavelength. And the decay is given by the density over the viscosity parameter. So just by putting the natural analogs for fluid coming from gravitational waves, or from gravitational concepts, what you arrive is this. And this is nothing but the Reynolds number in fluid dynamics. So you encounter that the equations that determine general relativity, hidden in it, intrinsically, have something that very much like with fluid, and this is something that is not the first time has been discussed, but it also points strongly to nonlinearities being present regardless, and it will do something like this. It's going to be channeling energy from one mode into another preferentially. So let me just summarize here. So there are compelling indications, in my point of view, that general relativity in the area ring down is not linearly stable. I have hopefully identified several mechanisms for you that channel nonlinearities actually do some interesting things. Further modes be created, modes varying in time, and not be cleanly represented in these ways. I argue, even though I didn't go into too much detail, that the relevant time scales are such that are commensurate with the source time. So source time and the relevant time scale for the decay are the same. If this black hole were decaying at a much faster rate than, say, this waveform here, then you could perhaps say, well, I already have my Kerr solution, and I can imagine the rest is perturbation. But the lifetime of this and the lifetime of the decay of this perturbed black hole are about the same. So we are in that intermediate regime where the interaction is non-trivial. So, but I told you at the very beginning, we have the evidence. There were these two claims. So what am I saying? Am I pushing back? But what am I pushing against? I'm not pushing against the fit. I have absolutely no problem that you can do a better fit with overtones than with just the fundamental ones. But I'm very strongly against the overinterpretation, which is to say that the fact that I can do this better fit implies that the system is behaving linearly, implies that the spin and mass that I'm measuring are the mass and spin of the black hole. I think it's just an artifact of the fact that of what I pointed before. that the overtones all have more or less the same oscillatory frequency. They have, however, a very much faster decay. And so whatever off I am in amplitude, I can add these overtones to just shave off the little bit that I'm missing, very much like what was already seen a long time ago here. This is the first and second order, and the other one was the first order. There is not significant difference in phase. There is just difference in amplitude. So what these overtones are giving me, by essentially for free, is an object that oscillates in the same frequency, but I can put here that will have no consequence there because it dies much faster. So that's what I think is going on. And with that, I will stop. Thank you.
Please, questions?
Hi. Yes. Thanks for the nice talk. So I have two questions. The first question is about observations. What would you need? What kind of an observation would you need to conclusively prove that this is what's going on? And
OK, so you want me to answer that? To conclusively, so I think that of course, I'm completely biased here, but I think I have conclusively proved that the system cannot be behaving linearly from the get-go. Already, you can do the second order calculation, and it's introducing some contribution. You can observe that your black hole there is changing its mass by, say, 1%. That will impact the description of modes. A pure mode will no longer be a pure mode. And here, this assumption relies on a pure mode stays a pure mode. You're just adding more overtones. So I think from I would flip it around. I think any extraordinary claim should be backed by extraordinary evidence. And I think there is no extraordinary evidence. And in front of this, I think there isn't a case. However, as I said, I have absolutely no problem whatsoever in saying this is a better fit. And it's convenient, and I think it's an artifact of the way these overtones are working.
And my second question is about a paper by Sean McWilliams from a few years back, which he also, I think, cited. So they claim to construct the waveform from the ring down backwards. According to this, it should be impossible. Would you agree with that, or no?
No, OK, so just to give a little bit of context, so I'm going to stop here. Yeah. No, let me put here. OK, so let me start first with this one. So I mentioned very quickly the photosphere. So the photosphere is almost the same as the innermost circular orbit, but for massless field, which of course include photons, but also gravitational waves or gravitons. There is a way to connect the location or the natural frequency associated to that with the quasi-null modes. So what does Sean do? So Sean is saying from after the merger, I can fit that behavior using that frequency. Of course, what he's doing explicitly is he says that in the paper, he's getting, in a sense, the quasi-null modes for free, built in. Then he uses an interpolating function between the crossing, say, of the innermost circular orbit or the photosphere to the peak of the waveform to merge with the earlier behavior. But what I'm saying is this doesn't preclude Sean. So Sean could choose to use early on a collection of overtones, and the fit will very likely be better. So I have no problem, as I said. This result, I mean, this is really good job. It's a very careful job. That is saying, if you keep adding these things, you're doing a better match. And that I have no issue with. I do have problems if someone wants to use that and say, this implies the system is behaving linearly.
So thanks for the talk. You told us that the frequencies are kind of similar, but the
Decay
doubling
rate.
time is different. But with better precision in the black hole spectroscopy, we could distinguish between just, I mean, what you told is happening and what people are telling us.
Oh, yeah, you're absolutely right. So in fact, what you do, I mean, so nowadays, going back to here, so there is another plot. Yeah, so let me say two things. There's another plot in this work that basically says, so if everything behaves linear from here onwards, well, let me use the first stupid example first. When I take a snapshot, when I take a selfie, which I don't do, but if I take a selfie, my face is represented by a whole bunch of Fourier modes. Of course, I think I'm not a collection of Fourier modes. But then when I move it a little bit, there would be a time dependence of those coefficients. So if the system were behaving linearly, and I do something at t equal 10, my choice of parameters will uniquely fix everything afterwards. So if I match at 10, and then I choose to match at 40, I should extract exactly the same coefficients, if there is signal left. The problem is that we're also fighting the fact that the signal is dying, so the SNR decreases. And there is some evidence that these coefficients are fluctuating. So already that's hinting at what you're saying. Eventually, if I have, whatever, LIGO of 25th generation or 25th generation detector, my SNR will be so low that I will be able to tell, and that will pick it up. Yeah, so it's funny that, so we're having this discussion now because the other detectors are not available yet, but eventually we're going to go there.
Yes.
But yeah, thank you.
Okay. Going once, going twice.
Ricardo?
So thanks for the talk. I wanted to ask if you could describe a little bit more about how to treat non-linearities in the early ringdown regime, if you use like hydrodynamic techniques to treat turbulence in fluids that are not in the relativistic region.
Beautiful question. I hope I knew the answer to that. So short of doing the simulation and getting them, there is something else, however, which is hinted a little bit on this work, but also on the work of turbines. So there is usually the eddy turnover time. So there is more than one time. And so there is something that I know people have been relatively successful with in some regimes, is to say, you go back to this equation, you still assume that these things are put, but now you promote these guys, the coefficient, to be time dependent. So this is going back to the previous question. But they are time dependent in a different time. It's a second time. So it's like, 2-time scale expansion. So then you put this back into the equations, and you obtain an equations for the coefficient. And then what you find out is that there is, of course, a nonlinear interaction is manifested now in the equation of motion for the coefficients themselves. And you can reveal the second time scale there, and what you're then able to capture is how energy is transferred from one mode into the other one in the right regimes. And this, what we did here is essentially that, but in a much simpler system. Where we can do that in general, that would be a complicated thing. Now, what Lars Berna and Paulo Bosch are exploring with is to just pick the fundamental mode, have just the A0 here, so go back to that one, but promote these guys to slowly varying coefficients. And they do that because they say, well, but we know the mass and spin will change. So can we have a fiducial or sufficiently simple but supported time dependence for this guy that then we can exploit for the fitting? And it seems to be, I've only seen preliminary work, that they can do as good a job as this one with perhaps just a couple fewer parameters. But what they are doing is just now capturing that slow variation that is, is happening on the physical grounds, and then this gives you a couple more parameters that then you can fit. But I wish I knew the answer to your question.
Okay.
Nathan?
answered it, but maybe I want to be more explicit. So if I understand correctly, you're saying that gravity waves today cannot capture linear deformations of black holes, right? That you, once you get to the linear part, you lose the signal.
Okay. Yes, great question. Let me try and answer in a slightly different way. So this is not the waveform, but just because it shows it clearly. So suppose the merger happens somewhere time there. So it decays very fast. Given today's sensitivity, you can only capture, in a way that no one else will dispute, for some sources, the fundamental mode. I think most sources, they haven't even captured the fundamental mode. But the very first one, and there are a couple more that has an SNR of 20 or 30 or thereabouts, the fundamental mode, the L2, M2 mode that happens afterwards, has been captured. The next one is just decay so much faster that you don't capture. And that's the beauty of this L2 mode, the one, this one overtones. They're not decaying as fast. So you have two, let me just go to Bertie's thing. You have two options. You can say, I'm going to capture different L's. I mean, first, the system, unfortunately, or fortunately, is being driven by a very specific thing. So it's an M2 mode, and these two obviously are going away. Also, the systematic or the observational bias that LIGO has, so, or the gravitational wave detectors have, is they will detect the strongest sources. The strongest sources are given by the equal mass binary case. And so you're driving with the M2, and the larger the L is, the faster it's decaying. So it gets more difficult. And so for these modes, especially that one, this one is not decaying as fast as the L equal. Well, first, the L equal 3 mode, because you're in the equal mass case, is not strongly sourced, while the L2 mode is sourced. This is why the very interesting choice was made by these groups, is to go after the overtones as opposed to all the L's. The traditional black hole spectroscopy that people had been discussing was to go after the L's. And for that, well, the first claim was that you need to wait for LISA to fly to have sufficient SNR. But the potentially saving grace is that if you're thinking that the theory is GR has no intrinsic scale. So in principle, you could stack many, many signals. So we had a work some years ago where you say, well, maybe you don't have to wait for LISA or third generation detectors. You just have to suitably stack them if you have several hundreds events, but we're on the way there. So maybe we don't have to wait for LISA, but for seeing clearly in a single signal, we either need a binary black hole merger at the other end of the corner, or we need much better detectors.
Okay, last call for questions. Then before we move to coffee, let's thank Luis again. The ones who did the study with the varying omega.
With what?
With the varying omega, with the time dependency omega.
Laura Sperner.
Ah, okay.
And Pablo Bosch.
Okay. They are at perimeter. No, where are they?
No, Laura now, she's at AI. And Pablo is